Proceeding with our discussion on the exercise of tracing and defining or determining the uniaxial stress strain path of the concrete as well as the pre-stressing steel in the pre-stressed concrete bar we may continue the discussion by first summarizing the results or the relationships that were derived for the increment or the change in the actual average applied stress in the concrete to the change or increment in the average actual applied stress in the steel due to the increase in the externally applied tensile force or external tensile loading denoted as capital T from the value of 0 to the point at which the concrete in the pre-stressed concrete bar cracks upon the application of the externally applied tensile force T highlighted as the red straight line in the plot of the uniaxial stress strain path of the concrete displayed in the graph presented in one of the earlier slides and marked by the pink arrow representing the uniaxial stress strain path traversed by the concrete in the pre-stressed concrete bar due to the externally applied tensile force or the external tensile loading denoted as capital T. Summarizing the salient results from the derivation of the equations relating the increase or change, that is increment in the average applied axial stress in the concrete of the pre-stressed concrete bar to the increment or change in the average applied axial stress in the pre-stressing steel bar by the virtue of the external tensile force or external tensile loading, capital T, the most useful or significant relationships are presented in the present slide right in the beginning. And as one can note from these final equations expressing the relationships the increment or the change in the axial tensile stress in the pre-stressing steel denoted as delta sigma subscript s, where the prefix delta signifies the increment or the change, while the notation sigma, as usual, represents the axial or normal stress. Subscript s denotes that the increment or the change, delta sigma, is in the axial tensile stress of the pre-stressing steel, equals the modular ratio, that is the ratio of the moduli of the pre-stressing steel to that of the concrete in the pre-stressed concrete bar, times the increment of the change in the average applied axial tensile stress in the concrete only due to the application of the externally applied tensile force T, that is denoted as delta sigma C, where the prefix delta signifies the increment or the change, while the notation sigma represents the average applied actual tensile stress, and the subscript C signifies that the average applied tensile stress is in the concrete of the pre-stressed concrete bar. Further, the increment or the change in the average applied actual tensile stress in the concrete only was found to be related to the average applied tensile stress due to the externally applied tensile force or the external tensile loading denoted as capital T in the pre-stressed concrete bar as a whole by this equation, which can be rearranged to arrive at a more familiar form of the relationship, that is the relationship between the increase or increment in the average applied tensile stress in the pre-stressed concrete bar as a whole disregarding the steel reinforcement, considering the gross cross-sectional area of the pre-stressed concrete bar, that was shown to be equal to 1.08 times, that is 108% of the increment or the change in the average applied axial tensile stress in the concrete only of the pre-stressed concrete bar due to the application of the externally applied tensile force T. With that summary on the results of the relationships or equations relating the increase in the average applied axial stress in the pre-stressing steel of the pre-stressed concrete bar to that in the concrete of the pre-stressed concrete bar, and further the equation relating the increment or the change in the average applied axial stress in the pre-stressed concrete bar as a whole based on the gross cross-sectional area of the pre-stressed concrete bar, disregarding the reinforcement, that is the increment or the change in the average applied axial stress in the pre-stressed concrete bar based on the nominal concrete section with the increment or the change in the average applied axial tensile stress in the concrete only of the pre-stressed concrete bar, under the application of the externally applied tensile force or the external tensile loading T, as the externally applied tensile force T increases from 0 to the value that is required or that causes the cracking of the concrete in the pre-stressed concrete bar, highlighted by the pink arrow in the plot of the uniaxial stress-strain path of concrete in the pre-stressed concrete bar, displayed in the graph presented in an earlier slide. Recall that based on the concept of equivalent or transformed concrete section that we have studied in the basic undergraduate course in concrete structures, in the second year of the undergraduate curriculum, the equivalent or the transformed concrete area in a reinforced concrete section, that is the RC section, can be expressed as A subscript E, denoting the equivalent or transformed concrete section, equal to the area of the gross concrete section or the nominal concrete section, denoted as A subscript C, simply given as the width times the overall depth of the concrete section plus the modular ratio M, that is the ratio of the moduli of elasticity of the steel to the concrete, minus 1 times the area of the steel, where the subtraction minus 1 is to account for the fact that the area of the steel has been considered twice, that is, in the gross cross-sectional area or the nominal concrete area, as well as the second term. In other words, for a rectangular concrete section with cross-sectional dimensions of width B and overall depth D. The equivalent or transformed concrete section, or the equivalent area or the transformed area of the concrete section in a reinforced concrete bar or a prestressed concrete bar may be expressed as A subscript E equal to the gross or the nominal area of the concrete cross section plus the modular ratio -1 times the area of the reinforcing steel or the pre-stressing steel, where the -1 is to account for the fact that the area of the pre-stressing steel or the reinforcing steel has already been considered in the gross or the nominal cross-sectional area of the concrete section denoted as A subscript C. Thus, the average tensile stress in the concrete or its increment, that is, the increment or the change in the average applied actual tensile stress in concrete denoted as delta sigma C, may be related to the change or the increment in the externally applied tensile force or external tensile load T, denoted as delta T, divided by the transformed or the equivalent concrete area based on the concept of the equivalent or transformed concrete section that we have all studied in the second year of the undergraduate curriculum in the course based on concrete design. Rearranging the terms, one can relate the increase or the increment in the average applied tensile stress in the concrete only, denoted as delta sigma C, in the reinforced concrete bar or the pre-stressed concrete bar, as the relationship given by equation A, that is, dividing the numerator and the denominator in the relationship herein by A subscript C, one can relate the increment or the change in the average applied tensile stress in the concrete alone or only by itself in case of the reinforced concrete bar or pre-stressed concrete bar, denoted as delta sigma subscript C, as equal to the expression labeled as equation A in the present slide. recognizing or noting that the numerator, that is the increase or increment or the change in the externally applied tensile force denoted as delta T, divided by the gross or the nominal cross-sectional area of the reinforced concrete bar or pre-stressed concrete bar, that is delta T divided by AC, is defined as the increase in the average applied axial stress in the reinforced concrete bar or the pre-stressed concrete bar considered as a whole, disregarding the steel, that is denoted as sigma, delta sigma subscript AV, and defining a new parameter, that is the steel ratio, or rather a parameter noting that the steel ratio by area of the reinforced concrete bar or the pre-stressed concrete bar already defined and denoted as rho equal to the ratio of the steel area to the gross or the nominal concrete area, one can arrive at a compact relationship between the increment or the change in the average applied axial stress in the concrete only of the reinforced concrete bar or the pre-stressed concrete bar, denoted as delta sigma C, with the increment or the change in the average applied axial stress in the reinforced concrete bar or the pre-stressed concrete bar considered as a whole, disregarding the reinforcement by means of this equation. Substituting the values of the modular ratio, that is the ratio of the moduli of the reinforcing steel or the pre-stressing steel as applicable, M, and the steel area ratios or the steel ratio in the reinforced concrete bar or the pre-stressed concrete bar by area, denoted as rho, into this equation derived on the basis of the concept of equivalent or transformed concrete section, one can arrive at the same relationship once again between the increase or increment or the change in the average applied axial stress in the concrete only of the reinforced concrete bar or the pre-stressed concrete bar as applicable to the increment or the change in the average applied axial stress in the reinforced concrete bar or the pre-stressed concrete bar as applicable, considering the reinforced concrete bar or the pre-stressed concrete bar as a whole, disregarding the reinforcement under the action or application of the externally applied tensile force T. Thus, the relationships or the equations relating the increase or increment or the change in the average applied axial stresses in the concrete only of the pre-stressed concrete bar with the increment of the change in the average applied axial stress in the pre-stressing bar as a whole under the action of the externally applied tensile force have been verified and found to be exactly the same as determined from the concept of equivalent or transformed concrete section. Further, as discussed earlier, strain compatibility requires that the change or the increment in the average applied strain in the reinforced concrete bar or the pre-stressed concrete bar as a whole, disregarding the individual constituent materials, that is concrete or the pre-stressing steel, by the virtue of the compatibility of strains between the concrete and steel should be equal to both the increment of the change in the average applied axial strains in the concrete only, as well as the increment or the change in the average applied strain in the pre-stressing steel or reinforcing steel as applicable. Based on the universally applicable principle of compatibility of strains or kinematics, the relationship obtained or derived on the basis of the equivalent or transformed concrete section can be further substituted into the general equation for the compatibility of strains between the concrete and the steel of the pre-stressed concrete bar or the reinforced concrete bar to arrive at the same relationship that was earlier derived between the increment of the change in the average applied actual stress in the pre-stressing steel and the average applied actual stress in the concrete. Labeled as equation number B in the present slide. Thus verifying the validity of the equations or relationships derived in the previous slides using the concept of equivalent or transformed concrete section. Further rearranging terms in equations A and B, and applying both the equations A and B, one can also verify or validate the third relationship or the third equation that was derived in the previous slide, that is the relationship between the increment of the change in the average applied actual stress in the pre-stressed concrete bar or the reinforced concrete bar as applicable, considered as a whole, disregarding the reinforcement, as equal to 1 plus m minus 1 rho times the increment of the change in the average applied actual stress in the concrete only of the pre-stressed concrete bar or the reinforced concrete bar, where substituting the values of the modular ratio m and the steel area ratio rho, one can easily verify that this equation, based on the concept of equivalent or transformed concrete section, results in the same relationship or equality as that derived in the previous slide. Hence, after summarizing and verifying the relationships or the equations derived in the previous slide between the increment or the change in the average applied actual stress in the steel to that in the concrete only of the pre-stressed concrete bar to that of the pre-stressed concrete bar considered as a whole, based on the nominal or gross concrete area, disregarding the reinforcement. We will now proceed to the next stage of the exercise in tracing and defining the uniaxial stress strain part of the concrete in the pre-stressed concrete bar as part of the solution to the illustrative numerical example for which the question statement was presented in one of the earlier slides. Well, the stage 3 of the uniaxial stress strain behavior of concrete in the pre-stressed concrete bar is defined as the state of cracking of concrete, that is, the state of stress and strain at which the concrete cracks. In other words, the stage 3 is identified as the stage in the uniaxial stress strain behavior of the pre-stressed concrete bar at which the first cracking of concrete occurs in the pre-stressed concrete bar, and based on the data on the material properties provided in the question statement of the assignment number 1, as well as the illustrative numerical example for which the question statement is presented in one of the previous slides, the cracking strain or the strain, that is the average axial applied tensile strain corresponding to the cracking of concrete is 0.0002, that is 0.02%, while the cracking stress or the cracking strength of concrete, also known as the modulus of rupture of concrete, that is more or less material property, an inherent material characteristic of concrete, along with the cracking strain. And is given as 2 MPa in the question statement of the illustrative numerical example presented in an earlier slide. Therefore, to arrive at the cracking strain of concrete, an inherent material property of concrete given as 0.0002 or 0.02%, from the pre-strain or the pre-compressive strain that is induced in the concrete by virtue of the pre-stressing operation and calculated as minus 0.0005 in the design calculations for stage 1 in a previous slide, where the minus sign signifies that the pre-compressive strain or the pre-strain in the concrete induced by the virtue of the pre-stressing operation is compressive in nature. the increment or the change in the average applied axial strain in the concrete from the limit state of the pre-stress concrete at the end of the pre-stressing operation to the stage of cracking, that is the stage 3, at which the concrete in the pre-stress concrete bar cracks, can be simply calculated as 0.0002 minus negative 0.0005 equal to 0.0007. Thus implying that the increment of the change in the average axial applied stress in the concrete only of the pre-stressed concrete bar that is required to crack the concrete or arrive at the stage of cracking of concrete, that is stage 3, from the initial state of pre-stressing, that is the initial pre-stress state at the end of the pre-stressing operation, is equal to 7 MPa. In other words, the increment or the change in the average applied axial tensile stress in the concrete only of the pre-stressed concrete bar that is required to cause or initiate the first cracking of concrete identified as stage 3 in the uniaxial stress strain behavior of the pre-stressed concrete bar from the point of or the stress strain state corresponding to the pre-stressed concrete at the end of the pre-stressing operation, that is after the completion of the pre-stressing operation, may be simply calculated as 7 MPa. Considering that the slope of the straight line portion of the uniaxial stress strain curve of the concrete, also defined as the elastic modulus of concrete is 10 to the power 4 MPa as calculated in one of the previous slides. Therefore, the increment or the change in the average applied axial tensile stress due to the application of the externally applied tensile force T denoted as delta sigma subscript C equals the increment or the change in the average applied axial strain in the concrete from the point of the initial state of pre-stress and pre-strain to the cracking strain times the elastic modulus of concrete determined earlier or calculated earlier in one of the previous slides, thus resulting in the value of the increment or the change in the average applied axial tensile stress in the concrete only of the pre-stressed concrete bar as 0.0007 times 10 to the power 4 calculated as 7 MPa. Due to the increase in the externally applied tensile force from 0 to the value T subscript CR required to crack the concrete or initiate the first cracking of concrete in the pre-stressed concrete berm. The corresponding change or increment in the strain or the average applied axial strain in the pre-stressing steel, that denoted as delta epsilon S, by virtue of strain compatibility should equal the corresponding increment or the change in the average applied axial strain in the concrete. During the application of the externally applied tensile force T or external tensile loading denoted as capital T, therefore, the absolute strain in the pre-stressing steel at the point of cracking of concrete, that is at stage 3, denoted as epsilon subscript S superscript CR, where the superscript CR signifies cracking of concrete, may be simply calculated as the strain, that is the average axial strain in the pre-stressing steel, denoted as epsilon SP, plus the change or increment in the average applied axial strain in the steel under the application of the externally applied tensile force. Or the external tensile load, capital T, up to the stage 3, that is the point of cracking of concrete. Therefore, adding the pre-strain or the pre-tensile strain in the pre-stressing steel induced by the virtue of the pre-stressing operation to the increment of the change in the actual applied strain in concrete, in steel rather, steel, denoted as delta epsilon s, where the prefix delta signifies the increment of the change, while notation epsilon signifies strain, and subscript s denotes that the increment of the change, delta epsilon, is in the pre-stressing steel due to the application of the externally applied tensile force T when added to the pre-strain or the pre-tensile strain in the pre-stressing steel by virtue of the pre-stressing operation results in the value of the actual tensile strain in the pre-stressing steel at the point of cracking of concrete, denoted as epsilon subscript s superscript cr, as equal to 0.00623 plus 0.0007, resulting in value of 0.00693. It is worthwhile to note here that one should check that the average applied actual tensile strain in the pre-stressing steel at the point of cracking of concrete does not exceed the yield strain of the steel, and as calculated in one of the earlier slides, the yield strain of steel based on the given yield stress of the pre-stressing steel and the Young's modulus of steel was found to be 0.0083, which is more than or greater than the average applied actual tensile strain in the pre-stressing steel at the point of cracking of concrete. Thus, it is confirmed or verified that the pre-stressing steel does not yield up to the point of cracking of concrete, or rather is far from yielding at the point of the first cracking of concrete in the pre-stressed concrete burn. Proceeding further, the stage 3 in the uniaxial stress strain behavior of the pre-stressed concrete bar is a stage of discontinuity in the uniaxial stress strain response of the concrete in the pre-stressed concrete bar, since stage 3 in the uniaxial stress strain behavior of prestressed concrete bar is defined as the cracking of concrete, or the point at which the first cracking of concrete occurs. And since cracking is a material discontinuity, that is a discontinuity in the material, one can expect an obvious discontinuity in the uniaxial stress strain curve of the material also. In other words, cracking of concrete being a discontinuity in the material continuum intuitively should result or cause in a mathematical discontinuity. Also, and the discontinuity appears in the uniaxial stress strain curve, or the uniaxial stress strain path of the concrete in the prestressed concrete bar at the point of cracking, as we will verify or substantiate in the next slide. The stage 3 at which the concrete cracks, or the first cracking of concrete occurs in the prestressed concrete bar, results in a mathematical discontinuity in the uniaxial stress strain curve, or the uniaxial stress strain response of concrete in the prestressed concrete bar, as predicted intuitively. As a result, the average applied axial tensile stress and the corresponding externally applied tensile force T that is measured immediately prior to the cracking of concrete is different from the average applied axial tensile stress, or the corresponding externally applied tensile force T that is measured or observed for the prestressed concrete bar subsequent to cracking. In order to treat this discontinuity in the externally applied tensile force T that is measured or recorded immediately prior to cracking, and that recorded or measured immediately after cracking, one has to consider the uniaxial stress strain response of the pre-stressed concrete bar in pieces, that is, in a piecewise manner, since the uniaxial stress strain response or curve of the pre-stressed concrete bar is not continuous across the point of cracking of concrete. However, the uniaxial tensile stress strain curve of the concrete in the pre-stressed concrete bar is piecewise continuous. That is, continuous in pieces. Essentially, piecewise continuity means that the response, in this case the uniaxial stress strain response of the pre-stressed concrete bar, is continuous prior to the point of cracking, that is prior to the point of discontinuity, a state that we will mention or label or define as the pre-cracking state, and is also continuous immediately after the point of cracking or the point of discontinuity. The state after the point of cracking or point of discontinuity will be defined as the post-cracking state in the present exercise. At the point of cracking, however, we have a discontinuity in the uniaxial stress strain response of the concrete in the pre-stressed concrete bar, fundamentally due to the discontinuity in the material that is caused by the cracking of concrete, that is essentially a separation or discontinuity in the material continuum. Focusing on the pre-cracking state or treating the uniaxial stress strain response of the concrete in the pre-stressed concrete bar immediately prior to cracking, that is, as the externally applied tensile force T approaches the cracking tensile force denoted as TCR, T or T subscript CR, superscript minus, where the notation T obviously denotes the externally applied tensile force. The subscript CR denotes that the value of the externally applied tensile force is T is the value required for the first cracking of concrete, while the superscript minus signifies that the externally applied tensile force approaches the limiting value of the cracking tensile force from the lower end or the lower side, or is less than the cracking tensile force. That is, the externally applied tensile force is differentially less than the cracking tensile force TCR by a differential quantity delta T, where the prefix delta signifies the differential nature of the quantity, while capital T signifies the externally applied tensile force. So therefore, in the pre-cracking state, that is the state of stress and strain when the cracking is imminent, that is immediately prior to cracking, mathematically described as the externally applied tensile force capital T equal to the cracking tensile force T subscript CR minus delta T, where delta T tends to 0. The measured cracking stress or the fracture strength of concrete in the pre-stressed concrete bar with reference to the absolute or original frame of reference can be calculated as presented in the next slide. It may be noted in the context of the discussion so far on the exercise of tracing and defining the uniaxial stress strain path of the concrete in the pre-stressed concrete bar, that the measured cracking stress, that is the apparent or the observed cracking stress or the fracture strength of concrete in the pre-stressed concrete bar is measured with reference to the shifted or transferred coordinate axis x dash y dash with the shifted origin O dash since the strain gauges are installed on the pre-stressed concrete bar for measurement of the average applied axial strains prior to the pre-stressing operation, while the externally applied tensile force T is measured or applied at the end of the pre-stressing operation. Thus, the measured cracking stress or the measured or observed cracking strength or fracture strength of concrete in the pre-stressed concrete bar with reference to the shifted or the transferred coordinate axis x dash y dash with the origin O dash is equal to the increment or the change in the average applied axial tensile stress delta sigma subscript AV in the pre-stressed concrete bar, also equal to the cracking value of the externally applied tensile force or the externally applied tensile force required to cause the cracking of concrete divided by the gross or the nominal cross-sectional area of the pre-stressed concrete bar. Simply because the externally applied tensile force, denoted as capital T, increases from 0 at the shifted origin for the transferred coordinate axis or frame of reference x dash y dash to the cracking value or the value of the externally applied tensile force T at the first cracking of concrete. However, one should note that the real or actual stress strain path of the concrete is the same regardless of the pre-stressing of concrete. That is, the real or actual stress strain path of concrete is an inherent material characteristic of concrete and does not vary due to the pre-stressing since the real or actual stress strain path of concrete depends only on the material properties of concrete, the stress strain path remains the same regardless of whether the concrete is pre-stressed or reinforced. However, the pre-stressing operation, that is, the pre-stressing of steel in the pre-stressed concrete bar, shifts or transfers the coordinate axis or the frame of reference for the measurement of the cracking stress from the original coordinate axis xy with the origin O to the shifted or transferred coordinate axis x dash y dash with the origin O dash, thus enhancing the measured or the observed cracking stress of concrete. With reference to the graph displaying the plot of the uniaxial stress strain response of concrete for the pre-stressed concrete bar as well as the reinforced concrete bar and the plain concrete bar of identical geometry and grade of concrete. The real or actual stress strain path of concrete is displayed by the green curve, which is universally applicable for the inherent material characteristics of the concrete, irrespective of whether the concrete is pre-stressed, as in case of a pre-stressed concrete bar, or reinforced, as in case of a reinforced concrete bar, or unreinforced, as in case of the plain concrete bar. In a nutshell, pre-stressing of concrete does not alter the actual or the real stress strain path of concrete, but the measured or apparent cracking stress or the tensile strength of concrete is enhanced by the virtue of the pre-stressing operation in the pre-stressed concrete bar due to the shift or transfer in the coordinate axis or the frame of reference for measurement of the externally applied tensile force from the original frame of reference xy to the shifted or transferred coordinate axis x dash y dash. In summary, the pre-stressed concrete or pre-stressing of concrete enhances only the measured apparent value of the cracking stress or the cracking strength, also termed as the fracture strength of concrete. Due to the shift or transfer of the coordinate axis by virtue of the pre-stressing. Continuing with our exercise of tracing and defining the uniaxial stress-strain path of the concrete in the pre-stressed concrete bar, recall that the measured or the apparent cracking stress or fracture strength of concrete in the pre-stressed concrete bar with reference to the shifted or transferred coordinate axis x dash y dash by the virtue of the pre-stressing operation can be calculated or was shown to be equal to 7 MPa. That is, with respect to the shifted or transferred frame of reference defined by the transferred coordinate axis x dash y dash based on the assumption that the strain gauges are installed on the concrete in the pre-stressed concrete bar prior to the pre-stressing operation. And therefore, the average applied axial tensile stress in the pre-stressed concrete bar considering the pre-stressed concrete bar as a whole based on the gross section or the nominal sectional area of the pre-stressed concrete bar, ignoring the reinforcement, denoted as delta sigma AV, where the prefix delta signifies the change or the increment in the average applied axial tensile stress due to the application of the externally applied tensile force T. The notation sigma, as usual, represents the axial or the normal stress in the pre-stressed concrete bar, while the subscript AV signifies that the increase or increment or the change, delta sigma, is calculated for the gross cross-section or the nominal section of the pre-stressed concrete bar, ignoring the pre-stressing steel, that is based on the overall cross-sectional area of the pre-stressed concrete bar, A equal to B times D in case of a rectangular cross-section for the pre-stressed concrete bar, as in this case, where B is the width while D is the overall depth of the pre-stressed concrete bar. Hence, the measured or the apparent cracking stress or the fracture strength of the concrete in the pre-stressed concrete bar, based on the average applied axial tensile stress that is required to crack the concrete, was related to the average applied tensile stress in the concrete only of the pre-stressed concrete bar, denoted as delta sigma subscript C, by this relationship which was derived in the previous slide as one of the salient or useful relationships based on considerations of statical equilibrium, compatibility of strains for the cross-section of the pre-stressed concrete bar. Substituting the values of the modular ratio and the steel area ratio, that is the area ratio of the pre-stressing steel, rho, the relationship between the average applied axial tensile stress or its increment for the pre-stressed concrete bar can be related to the increment or the change in the average applied axial tensile stress in the concrete only of the pre-stressed concrete bar as 1.08 times the increment or change in the average applied axial tensile stress in the concrete only of the pre-stressed concrete bar. As derived in the previous slide as one of the most salient or useful equations representing the relationship between the increments or the changes or the increase in the average applied tensile stress of the pre-stressed concrete bar and the increment or the change in the average applied axial stress in the concrete only, as well as the increment or the change in the average applied axial tensile stress in the pre-stressing steel, all of which equations were derived in the previous slide based on considerations of statical equilibrium and strain compatibility or compatibility of strains for the cross section of the pre-stressed concrete bar. Hence, summarizing the results of the design calculations presented in the previous slide, the increment or the change in the average applied axial tensile stress for the pre-stressed concrete bar as a whole, based on the gross or the nominal section of the pre-stressed concrete bar, ignoring the pre-stressing steel, denoted as delta sigma subscript AV, can be related to the increment or the change in the average applied axial stress in the concrete only of the pre-stressed concrete bar due to the application of the externally applied tensile force T by this relationship, that is 1.08 times the increment or the change in the average applied axial tensile stress in the concrete only of the reinforced of the pre-stressed concrete bar due to the application of the externally applied tensile force T, thus resulting in a value of 1.08 times 7 MPa, that is 7.56 MPa for the increment or the change in the average applied axial tensile stress for the pre-stressed concrete bar as a whole, considering the gross or the nominal section of the pre-stressed concrete bar, ignoring the reinforcement, under the application of an externally applied tensile force T up to the point of cracking of concrete, which is therefore identified or defined as the measured or apparent cracking stress or fracture strength of concrete in the pre-stressed concrete bar. It is worthwhile to mention here that the value of 7.56 MPa that was calculated, or that is calculated based on the relationships or equations derived in the previous slide, for the average applied axial tensile stress due to the application of the externally applied tensile force T for the pre-stressed concrete bar as a whole is termed as the measured or apparent cracking stress, or the apparent measured fracture strength of concrete. The real or the actual cracking stress or fracture strength of concrete is an inherent material property and was calculated as 2 MPa as in case of the plain concrete bar without any steel reinforcement, pre-stressed or non-pre-stressed. It should be noted that the actual or the real cracking stress or fracture strength of concrete cannot be altered, as it is more or less an inherent characteristic of the material, that is concrete, as in case of the plain concrete bar. However, the pre-stressing operation in case of the pre-stressed concrete bar shifts or transfers the coordinate axis for the frame of reference for measuring the average applied axial tensile stress that is required to cause cracking of concrete in the pre-stressed concrete bar to the shifted coordinate axis x dash y dash with the shifted origin O dash. Hence, the average applied axial tensile stress or the increment or change thereof is measured as 7.56 MPa. From the point of application of the externally applied tensile force T to the cracking of concrete. However, it should be remembered that pre-stressing of concrete enhances only the measured or apparent cracking stress of concrete, or the measured or apparent fracture strength of concrete, by shifting the coordinate axis of the frame of reference for measuring the average applied axial tensile stress delta sigma subscript AV that is required to cause the cracking of the concrete. The real or actual cracking stress or fracture strength of concrete, or cracking strength of concrete, is still the same as in case of the plain concrete bar, that is 2 MPa, an inherent material property that cannot be changed. However, the pre-stressing operation enhances the measured or the apparent cracking stress or the cracking strength of concrete by shifting or transferring the coordinate axis of the frame of reference for measuring the increment or the change in the average applied axial tensile stress in the pre-stressed concrete bar to the shifted or transferred coordinate axis x dash y dash with the shifted origin o dash. Proceeding with the exercise of tracing, defining and plotting the uniaxial stress strain path of the concrete in the pre-stressed concrete bar, recall that the state of cracking of concrete, that is the limit state corresponding to the first cracking of concrete in the pre-stressed concrete bar, is a point of discontinuity in the uniaxial stress strain response of the concrete, simply because cracking or a crack itself is a discontinuity in the material continuum, or the material that is concrete. And as in case of any discontinuity, in the solution of the structural response, we have to consider the uniaxial stress-strain response of the concrete in the pre-stressed concrete bar across the point of discontinuity, that is, across the point of cracking of concrete in two pieces, since the discontinuity in the uniaxial stress-strain curve or the uniaxial stress-strain response of the concrete at the point of cracking can be dealt with by considering the uniaxial stress-strain response of the concrete in a piecewise continuous manner only. That is, the uniaxial stress-strain response prior to cracking has to be considered in a separate equation, while the uniaxial stress-strain response of the concrete in the pre-stressed concrete bar after the point of cracking, that is, the post-cracking state, has to be considered in another separate equation. Since the uniaxial stress-strain response of concrete in the pre-stressed concrete bar is discontinuous at the point of cracking of concrete, but is piecewise continuous, that is, continuous immediately prior to the point of cracking, that is, in the pre-cracking state, and also continuous immediately after the point of cracking of concrete, that is, in the post-cracking state. Hence, as in case of any discontinuous structural response, we need to consider the uniaxial tensile stress-strain response of the concrete in the pre-stressed concrete bar in the pre-cracking state as piecewise continuous and separate or discontinuous from the uniaxial tensile stress-strain response of the concrete in the post-cracking state. Mathematically, the equations expressing the relationship between the increments of the change in the average applied axial stress in the concrete only, and that in the steel only, as well as the average applied axial stress in the pre-stressed concrete bar as a whole in the pre-cracking state, that is immediately prior to cracking, assuming piecewise continuity prior to cracking, were discussed and presented in the previous slide. In the present slide, the relationships or the equations representing the relation between the increment or the change in the average applied axial stress in the concrete only to that in the pre-stressing steel, as well as that in the pre-stressed concrete bar considered as a whole, will be discussed in the present slide. For the post-cracking state of concrete, that is, the piecewise continuous state of concrete after the point of the first cracking of concrete. Mathematically, in the limit that the externally applied tensile force capital T tends to or approaches the value TCR, that is T subscript CR, which is the externally applied tensile force T required to cause the cracking of concrete from the higher end, that is from the positive or the higher side, which can also be expressed as the externally applied tensile force T equal to the value of the externally applied tensile force T at the point of cracking of concrete plus an increment or an incremental value of the externally applied tensile force T, where the increment denoted as delta capital T, in which delta, the prefix, signifies the increment in the externally applied tensile force capital T, where delta T tends to 0. In physical terms, the mathematical characterization of the externally applied tensile force implies the post-cracking state, that is, the state of concrete in the pre-stressed concrete bar immediately after the cracking of concrete, for which the concrete in the pre-stressed concrete bar is already cracked, having undergone the first cracking, and is therefore ineffective in tension. As a result, mathematically, the shear of the externally applied tensile force that is resisted by the concrete in the post-cracking state, that is, immediately after the first cracking of concrete, denoted as capital T subscript C, where the subscript C signifies the shear of the externally applied tensile force resisted by the concrete or the cracked concrete, is equal to 0. Consequently, the total externally applied tensile force T is resisted only by the pre-stressing steel. Condition that is mathematically represented by this equation, which implies that the externally applied tensile force capital T is equal to the externally applied tensile force that is resisted by the pre-stressing steel only. Since concrete is unable to resist or transmit any tensile stress immediately after cracking or upon the first cracking of concrete. As a result, the uniaxial stress strain state in the pre-stressed concrete bar post-cracking of concrete, that is, the post-cracking state, is dictated entirely by the pre-stressing steel, that is, the uniaxial stress and strain in the pre-stressed concrete bar is determined or governed only by the tensile stress in the pre-stressing steel. Since the uniaxial tensile stress or the average applied axial tensile stress in the pre-stressed concrete bar in the post-cracking state, that is, post-cracking of or after the cracking of concrete is dictated only by the tensile stress in the pre-stressing steel, as concrete is ineffective in tension and therefore unable to resist any tensile stress immediately after the point of first cracking of concrete. The derivation of the relationships for the average applied axial tensile stress for the pre-stressed concrete bar immediately after cracking, that is in the post-cracking state, are considerably simple in comparison to those in the pre-cracking state, as only the pre-stressing steel is effective in resisting the externally applied tensile force T, or the corresponding externally applied average tensile stress. Therefore, one may conclude for the post-cracking state that the average applied axial tensile stress of the pre-stressed concrete bar as a whole, based on the nominal or gross concrete section of the pre-stressed concrete bar, ignoring the area of the pre-stressing steel, denoted as sigma subscript AV superscript CR, where the superscript CR signifies the cracking limit state or the post-cracking limit state, that is, the limit state immediately after or post-cracking, is simply calculated as the axial tensile stress in the pre-stressing steel, denoted as sigma subscript S, times the area of the pre-stressing steel, denoted as capital A subscript S, divided by the gross or the nominal section A subscript C of the pre-stressed concrete bar as a whole, recognizing that the ratio of the area of the pre-stressing steel to the gross or the nominal cross-sectional area of the concrete or the pre-stressed concrete bar is defined as the steel area ratio, denoted by the symbol rho, the average applied axial tensile stress immediately after cracking, or immediately after the point of first cracking of concrete, denoted as sigma subscript AV superscript CR for the pre-stressed concrete bar in the post-cracking state is simply calculated as sigma S times rho, where sigma S is the axial tensile stress in the pre-stressing steel, while rho is the steel area ratio of the pre-stressing steel in the pre-stressed concrete bar. Further, the steel. Or the pre-stressing steel is in a completely different state of stress and strain in comparison to the concrete in the pre-stressed concrete bar, since the stresses or the strains in the concrete in the pre-stressed concrete bar are entirely different from those in the steel in the pre-stressed concrete bar. Therefore, it is important to trace, locate, and define the state of stress, that is axial stress and axial strain in the steel at all the different stages of the uniaxial stress strain response of the pre-stressed concrete bar, as well as the state of axial stress and strain in the concrete of the pre-stressed concrete bar. Noting that the strain specific, the axial tensile strain in the pre-stressing steel at the point of cracking was calculated as 0.00693 . The stress, that is the axial tensile stress in the pre-stressing steel of the pre-stressed concrete bar at the point of cracking or immediately after or the point of cracking in the post-cracking state can be obtained as the modulus of elasticity of steel, or the Young's modulus of steel, times the axial tensile strain in the steel calculated in the previous slide for the pre-stressed concrete bar at the point of cracking. Substituting the value of the applied tensile strain in the pre-stressing steel of the pre-stressed concrete bar at the point of cracking of concrete, that is immediately after the first cracking of concrete, the post cracking of concrete as 0.00693, one can calculate the average applied axial tensile stress for the pre-stressed concrete bar considered as a whole based on the nominal or gross section of the pre-stressed concrete bar, ignoring reinforcement, at the point of cracking of concrete or immediately after the point of cracking, that is in the post-cracking state, as sigma subscript AV superscript CR equal to 5.544 MP. Using the relationship derived for the average applied axial stress in the pre-stressed concrete bar based on the nominal or gross section of the pre-stressed concrete bar in the present slide. Thus, completing the design calculations for tracing, locating and defining the uniaxial tensile stress-strain path of the concrete as well as the pre-stressing steel in the pre-stressed concrete bar, we will now proceed to the next limit state in the uniaxial tensile stress-strain response of the pre-stressed concrete bar, that is identified by the yielding of steel, that is the yield point of the pre-stressing steel a stage identified as stage 4 corresponding to the yielding of steel in the present slide. And since the concrete in the pre-stressed concrete bar is already cracked and therefore ineffective in tension, that is the concrete at stage 4 corresponding to the yielding of steel is unable to resist any tensile stress at this stage. The uniaxial stress strain state of the pre-stressed concrete bar at the stage of yielding of concrete, that is stage 4, obviously after the cracking of concrete, is dictated only by the tensile stress in the steel. Specifically, since stage 4 is identified as the state of yielding of the pre-stressing steel, the uniaxial state of stress and strain in the pre-stressed concrete bar at the stage of yielding of steel, that is stage 4, is dictated by the yield stress of steel, denoted as sigma subscript Sy, where the subscript Y signifies yielding or the yield stress of steel, given as 1660 MPa, that is 1660 MPa, as calculated in a previous slide. Corresponding to the yield strain of steel, specifically the pre-stressing steel, calculated as 0.0083 in a previous slide. As mentioned earlier, we have to trace and locate the uniaxial stress-strain state not only in the concrete of the pre-stressed concrete bar, but also the uniaxial stress-strain state of the pre-stressing steel. A consideration that assumes particular significance at stage 4 of the uniaxial stress-strain response of the pre-stressed concrete bar, since the uniaxial stress-strain response of the pre-stressed concrete bar at the stage 4, corresponding to the yielding of the pre-stressing steel, is dictated only by the uniaxial stress-strain state of the pre-stressing steel. And considering the increment or the change in the uniaxial tensile strain in the pre-stressing steel, denoted as delta epsilon subscript S, where the prefix delta signifies the increment or the change. The notation epsilon denotes the axial strain as usual, while the subscript S signifies that the increment in the axial strain is in the pre-stressing steel. At the point of yielding of steel is equal to the yield strain of steel, calculated as 0.0083 in the previous slide, minus the strain in the steel at the point of cracking of concrete. calculated as 0.00693 from the point of cracking of concrete to the stage of yielding of steel, thus resulting in the total increment or the change in the uniaxial tensile strain in the pre-stressing steel from the stage 3 corresponding to the cracking of concrete to the stage 4 corresponding to the yielding of steel as 0.00137. Based on the consideration of compatibility of strains between the increment of the change in the uniaxial strain in the pre-stressing steel and the concrete in the pre-stressed concrete bar. Hence, the uniaxial average applied strain in the concrete of the pre-stressed concrete bar at the point or stage of yielding of steel, that is stage 4, denoted as epsilon subscript C, where the subscript C signifies that the strain epsilon is in the concrete of the pre-stressed concrete bar, while the superscript Y signifies that the strain epsilon C is at the point of yielding of the steel, that is at stage 4, corresponding to the yielding of the steel in the pre-stressed concrete bar, or yielding of the pre-stressed concrete bar due to the yielding of the pre-stressing steel, can be calculated by adding the increment or the change in the average applied axial strain in the concrete or that in the pre-stressing steel from the point of or stage of cracking of concrete that is stage 3 up to the point of yielding of steel or stage of yielding of the pre-stressing steel, that is stage 4, as the sum of the cracking strain of concrete, that is, the actual average tensile strain in the concrete at the point of cracking a material property given as 0.0002 plus the increment or the change in the average applied axial strain in the concrete, or also equal to the average applied axial strain in the steel from the point of cracking of concrete, that is stage 3, up to the point of yielding of steel, that is stage 4, resulting in a value of the average applied axial strain in the concrete at the point of or stage of yielding of concrete, of steel rather, that is stage 4, identified as this point of yielding of steel, as equal to epsilon subscript c superscript y, where the subscript c signifies that the average applied axial strain is in the concrete, while the superscript y signifies that the average applied axial strain in the concrete is at the point of yielding of steel, that is at stage 4, and is calculated as 0.00157. After having defined the uniaxial state of stress and strain in the concrete as well as the pre-stressing steel at the stage 4, that is the point of yielding of the pre-stressing steel, we will proceed now to the next stage in the uniaxial stress-strain response of the pre-stressed concrete bar under the application of an externally applied tensile force T. The next stage, that is stage 5, is identified in the uniaxial tensile stress strain curve for the pre-stressed concrete bar as the ultimate limit state. That is identified as the limit state at which the pre-stressed concrete bar fails due to the rupture of the pre-stressing steel. In other words, the next stage in the uniaxial tensile stress strain response of the pre-stressed concrete bar is the ultimate limit state of the pre-stressed concrete bar corresponding to the failure of the pre-stressed concrete bar identified by the rupture of the pre-stressing steel, or the ultimate strength, or that is the ultimate stress of the pre-stressing steel. Given the ultimate stress of the pre-stressing steel, denoted as sigma S subscript SPU, where the notation sigma denotes the actual stress as usual, while the subscript S signifies that the actual stress is for the pre-stressing steel, while the subscript P signifies pre-stressing steel, and the subscript U denotes the ultimate tensile stress or the tensile strength of the pre-stressing steel, given as 2075 MPa. And as in case of stage 4 or the post-cracking state of the pre-stressed concrete bar, since the concrete is already cracked and therefore ineffective in tension and unable to resist any tensile stress after the cracking, the ultimate limit state of the pre-stressed concrete bar, that is stage 5, is also governed by the state of stress and strain of the pre-stressing concrete, pre-stressing steel. In other words, since concrete has already cracked at the ultimate limit state of the pre-stressed concrete bar, as in case of stage 4 corresponding to the yielding of steel in the pre-stressed concrete bar, and the post-cracking state of concrete in the pre-stressed concrete bar, the concrete is therefore redundant or ineffective at the ultimate limit state of the pre-stressed concrete bar, that is stage 5, which is therefore governed only by the ultimate tensile stress and the corresponding ultimate tensile strain of the pre-stressing steel in the pre-stressed concrete bar. Consequently, the average applied actual stress in the pre-stressed concrete bar considered as a whole based on the gross or nominal section of the concrete bar, ignoring the steel reinforcement, denoted as sigma subscript AV superscript U, where the superscript U signifies that the average applied axial tensile stress is at the ultimate limit state or the failure of the pre-stressed concrete bar, can be calculated simply as the ultimate tensile strain, the ultimate tensile stress, denoted as sigma subscript SPU and given as 2075 or 2075 MPa for the pre-stressing steel, times the steel area ratio of the pre-stressing steel, denoted as rho and given as 0.004. Calculating the value of the average applied axial stress of the pre-stressed concrete bar considered as a whole, disregarding the pre-stressing steel based on the cross or nominal section of the pre-stressed concrete bar, ignoring the area of the pre-stressing steel, sigma A subscript AV superscript U is simply calculated as 2075 MPa, the ultimate tensile stress for the pre-stressing steel, times 0.004, the steel area ratio of the pre-stressing steel on the pre-stressed concrete bar, as resulting in 8.3 MPa. Tracing the strains that is the average axial strain in the concrete as well as the pre-stressing steel in the pre-stressed concrete bar from the point of yielding of steel or rather from the point of cracking of concrete to the ultimate limit state, that is stage 5, as mentioned earlier, since the strain, that is the average applied axial strain in the pre-stressing steel and the concrete in the pre-stressed concrete bar are completely different at any stage. Due to the pre-stressing operation, it is important part of the exercise to trace and define the average applied axial strains in the concrete as well as the pre-stressing steel at each and every stage of the uniaxial stress strain response of the pre-stressed concrete bar. Therefore, given the ultimate tensile strain corresponding to the ultimate tensile stress of the pre-stressing steel, in the question statement as 0.01 that is 1%, as the value of the ultimate tensile strain, which is the average axial tensile strain in the pre-stressing steel at the failure of the pre-stressing steel, that is at the rupture of the pre-stressing steel bar. The total change or increment in the applied axial tensile strain in the pre-stressing bar from the point of cracking of concrete, that is stage 3, to the ultimate limit state of the pre-stressed concrete bar, that is stage 5, may be calculated as delta epsilon subscript s equal to the ultimate tensile strain of the pre-stressing steel given in the question statement, denoted as epsilon SPU minus the applied tensile strain in the pre-stressing steel at the point of cracking of concrete, that is the stage 3. Thus calculated as 0.01 minus 0.00693, which is the strain or applied axial strain in the pre-stressing steel at the point of cracking of concrete or post-cracking of concrete, that is stage 3. Thus resulting in the value of the increment or change in the strain or the applied axial strain in the pre-stressing steel between the ultimate limit state of the pre-stressed concrete bar, that is stage 5, and the point of cracking of concrete or post-cracking state, that is stage 3, as equal to 0.00307. Correspondingly, the strain or the average applied axial strain in the concrete denoted as epsilon c subscript u, epsilon subscript c superscript u, wherein the notation epsilon denotes axial strain as usual. Subscript c signifies that the applied axial strain is in the concrete, while the superscript u signifies that the applied axial strain in the concrete is at the ultimate limit state. that is stage 5 of the uniaxial stress strain response of the pre-stressed concrete bar may be calculated as the sum of the cracking strain, that is the average applied axial strain in concrete at the point of cracking of concrete or at stage 3, plus the increment or the change in the strain of concrete or that of steel, both being equal by the virtue of strain compatibility, from the point of cracking of concrete, that is stage 3, to the point of the ultimate limit state, that is stage 5 of the pre-stressed concrete bar, given as or calculated as 0.00307 in the previous step, thus resulting in a value of the average applied axial strain in the concrete at the ultimate limit state of the pre-stressed concrete bar, denoted as epsilon subscript c superscript u as 0.00327. It is worthwhile to note here that the limiting values of the average applied axial stress and the average applied axial strain in the concrete as well as the steel and the pre-stressed concrete bar calculated in the present slide for stage 5, 4, and in the previous slide for stage 3, as well as stages 1 and 2 of the uniaxial stress strain response of the pre-stressed concrete bar completely define the uniaxial stress strain path of the concrete as well as the steel, that is pre-stressing steel, and the pre-stressed concrete bar as a whole. Further, it should be noted that the solution for part B of question number 1 of assignment number 1, that is the part based on the determination of the uniaxial stress strain part of the corresponding reinforced concrete bar which is to be located and plotted in part B of question number 1 of assignment number 1 is implicit or implicitly included in the present solved example. Since the stage 4 and stage 5 corresponding to the yielding of steel and the ultimate limit state of the prestressed concrete bar are exactly the same as those for the corresponding reinforced concrete bar. With the exception that the pre-strain or the pre-compressive strain in the concrete and the pre-strain or the pre-tensile strain in the pre-stressing steel and the corresponding pre-stress or the pre-compressive stress in the concrete and the corresponding pre-stress or the pre-tensile stress in the pre-stressing steel need to be treated as 0 while locating and defining the uniaxial stress strain part for the corresponding reinforced concrete part as the reinforcement, that is the steel reinforcement in the reinforced concrete bar, is not pre-stressed, and thus the pre-strain and the pre-stress in the reinforced concrete bar is equal to 0, 0. In other words, the uniaxial stress strain response of the reinforced concrete bar is a special case of the uniaxial stress strain response of the pre-stressed concrete bar for the condition that the pre-strain or the pre-compressive strain and the pre-stress or the pre-compressive stress in the concrete as well as the pre-strain or the pre-tensile strain in the steel are all specified as 0 in case of the reinforced concrete bar. In physical terms, the uniaxial stress strain response of the reinforced concrete bar, that is composed of identical grade of concrete with an identical geometry as that of the pre-stressed concrete bar, may be obtained by considering the uniaxial tensile stress strain curve or the uniaxial tensile stress strain behavior of the pre-stressed concrete bar with reference to the original coordinate axis, that is the original frame of reference defined by the coordinate axis x, y. Since the pre-strains and the pre-stresses in the concrete and steel in case of the reinforced concrete bar are both 0, and thus the coordinate axis for the frame of reference of the uniaxial stress strain response of the reinforced concrete bar does not shift from the original coordinate axis xy of the frame of reference for the plain concrete bar. In other words, the uniaxial tensile stress strain curve for the reinforced concrete bar that is to be determined in Part B of question number 1 of assignment number 1 can be simply obtained as the uniaxial stress strain curve for the pre-stressed concrete bar with reference to the original coordinate axis. X, Y. That is the frame of reference or the coordinate axis for the plain concrete bar. In conclusion, referring to the graph presented in a previous slide, illustrating the uniaxial stress strain curves for the pre-stressed concrete bar as well as the plain concrete bar and the reinforced concrete bar. The uniaxial stress strain response of the pre-stressed concrete bar is displayed with reference to the shifted coordinates or the transfer coordinates x dash y dash because of the pre-strain and pre-stress in the concrete of the pre-stressed concrete bar. However, the same uniaxial tensile stress strain curve is applicable or valid for a corresponding reinforced concrete bar composed of identical grade of concrete and identical geometry as the pre-stressed concrete bar, provided the plot of the uniaxial stress strain curve is viewed or considered with reference to the original coordinate axis or the original frame of reference x and y. Simply because the real or actual stress strain path of concrete as a material is the same being a material characteristic or an attribute of the material, that is concrete, and does not vary or alter by the pre-stressing operation.